harder to push the one which is confined, right? And because of that, the Young modulus is going to be smaller than the constraint modulus. Only in the event in which the Poisson ratio is equal to 0, these are going to be the same. For example, here, Poisson ratio equal to 0, this is 1, this is 1, this is 1, and this is equal to that. But in most cases, in which the Poisson ratio is not 0, the constraint modulus is going to be larger than the Young modulus. When you deplete a reservoir, the conditions of strains sometimes are very similar to the ones that we have over here. Because when you deplete a long and thin reservoir overlain by a cap rock, the rock is not going to extend in lateral direction. It's not going to get shorter also in lateral direction. It's just going to compress in vertical direction. Therefore, this same type of condition is going to be related to the bulk compressibility of the rock, and actually it's going to be the inverse of the bulk compressibility. And we're going to see also later how that is related to pore compressibility, which is the value that you need in reservoir simulation. We'll get back to that later on, okay? Because there's something very important we need to finish here before we run out of time. Okay, so very important equation relates strain to stress in vertical direction under constrained conditions with no lateral strength. Okay, let's now solve sigma 1,1 and sigma 2,2, which in our case now these are horizontal stresses. This is a value that we want to know in order to do many things, one of them hydraulic fracture. Okay, so I'm just going to use the equations. Sigma 1,1 from the equation there on top is going to be the first row times this column vector, and it's going to be the first two members are 0 because these are 0. The only one which is not 0 is this one. So this is going to be Poisson ratio times L09-3 times the Young modulus and the factor that was outside. I should have put it on the left. It's too late. It's the same. But from this equation, actually, I know what this strain is. That strain is the same as that one. So I'm going to replace now that value of strain related to vertical stress in here. And this is going to be Poisson ratio, and the strain is going to be, just I'm getting it from the equation above. That times sigma 3, 1 minus Poisson ratio divided by Young modulus. So this was strain, and this is what I had before. And if you notice in this equation, I have Young modulus here, Young modulus there. I have these terms with Poisson ratio, numerator and denominator. And the only thing that survives out of that is that sigma 1,1 is equal to Poisson ratio 1 minus Poisson ratio times sigma 3. And I can do the same for the other direction, and it's going to be exactly the same. And tells me that the effective horizontal stress is equal to Poisson ratio divided by 1 minus Poisson ratio the vertical effective stress. So this one is effective horizontal stress, and this one over here is effective vertical stress. And what goes in here, this parameter, is called an effective lateral stress coefficient. But don't worry about that name. It's just a coefficient that links the horizontal stress to the vertical stress. And in some way it tells you the capacity of the rock to expand sideways. So this is going to be very important. And because if we, under these conditions, if we know what is the value of Poisson ratio, we can tell what the horizontal stress is going to be. And in order to have a better idea about what that value can be, let's plot here effective lateral stress coefficient versus Poisson ratio. What are typical values of Poisson ratio that we said a couple of lectures ago? We said 0 to 0.5, cannot be larger than that. And if the Poisson ratio is 0, what is going to be the value of the effective lateral stress coefficient? 0. And if I have 0.5, 1, it's going to be equal to 1. And let's do an intermediate case. What about 0.25? It's going to be 0.25 divided 0.75, that's 1/3. So let me divide this in thirds. It's going to be a point somewhere over here. And this is going to be a line with a concave curvature. It's going to be something like this. But this is super important because it tells us how much rocks are pushing sideways as a function of the Poisson ratio or the capacity to expand laterally. Typical rocks, like sandstones, carbonates, have a Poisson ratio that goes from 0.1 to 0.25. Some other softer rocks, especially mud rocks, can have, especially if they are soft, they can have a bigger Poisson ratio. Shales, depending on how litified they are, could be somewhere over here. And depending on the type of rock, your lateral stress could be different. Let's do a few drawings to make a schematic of this. If I have a Poisson ratio equal to 0, that would mean that if I had a rock and I push it just with the stress vertical and in unconfined conditions, the rock would not expand at all to the sides. And because it doesn't expand at all to the sides, it's not going to develop lateral stress either. If I have a rock with a very large Poisson ratio, and if I push it vertically, that means that it's going to expand to the sides quite a bit. And when I get this in constrained conditions, that will develop a lot of stress to the sides. And something intermediate would be something that just expands a little bit to the sides when you load it vertically. So the capacity of rocks to expand laterally is going to control how much stress you get on horizontal direction. A rock with a very small Poisson ratio, it doesn't push to the sides at all. Even if it's 0, it doesn't push to the sides at all. So in that case, your horizontal vertical stress will be 0. But that's not the case of most rocks, almost all rocks. They all push a little bit to the sides. And for typical rocks, they're going to push with about 1/3 of their weight to the sides. If they have a very large Poisson ratio, they're going to push with all their weight to the sides. It's like a fluid. A fluid gets to a Poisson ratio close to 0.5. And we know that fluids, they have, when you have gravity, then you're going to have a pressure, and the pressure is going to be the same in all directions, right? And this is similar to this. When you get to 0.5, if you have a rock that expands laterally to the sides all the way, then the same stress that you get in vertical direction, you're also going to get it in horizontal direction. Do you know any case of a rock that has a Poisson ratio close to 0.5? There is one, and this is going to be the case of salt rocks. Salt rocks, it's a little bit more complex than that, and they have certain behavior which is called viscoplastic, and it is that they deform slowly, but they deform. And if you give it enough time, the same way that you put in vertical direction, you're going to get it in horizontal direction. I don't know if you guys are familiar with salt diapirs, but these are these salt structures that there is a huge deposit of salt at some time, then you put rock on top, and since the salt is less dense than the rock, it starts to flow up with time. It takes thousands, millions of years, but they do flow and they do deform, and that's because of their viscous nature. And in those cases, if you're within a salt dome, then your horizontal stress is going to be very similar to your vertical stress. And let me tell you something very recent. You know, as recent as research done in the last 2 years. It has been found that there are some rocks particularly shales or unconventional that tend to develop quite a bit of viscous deformation. And what that means is that when you apply vertical load, with time, slowly, they're going to creep in deforming to the sides or passing that stress from vertical direction to the horizontal direction, so that they may behave like a rock with a high Poisson ratio, and the result of that is going to be that your horizontal stress is going to be almost as high as your vertical stress. And that's going to be very important for hydraulic fracturing, because you're going to need a much higher pressure in order to make a hydraulic fracture. Okay, so with sigma 1,1, again, in our case, this was a vertical stress and effective, and sigma 1,1 and sigma 2,2 were, just one more second, guys, were effective horizontal stresses. The last step that we need in order to use this to do what is called stress law is get out of here the total horizontal stress. And we'll do that on Wednesday, and you'll be ready to complete the homework after we do this. All right? One reminder, there is no laboratory this week. There's going to be a laboratory next week. Okay? Take care.